So is the caterpillar's height above the ground a function of his time since he started walking? What do you think? If this is an image of related to that? Chime in whenever you want to. What do you think? Is caterpillar's height a function of a time elapsed since the caterpillar left point A? Everybody's here today? Okay. Anyone want to take a stab at this? Answer this question?
It's not a function.
Okay. Is that? Sarah?
Yeah.
Okay. Why not, Sarah?
Because it's asking if it's a function of the time elapsed, but we're given like the ground and then like the height above the ground, so it's like varying in the heights. It doesn't show like as time goes on what the height is.
Okay, so what you're noticing is that the variables mentioned in this question are different from the graph. Is that what you're saying? Okay, that's a
Yeah.
good observation. Okay, and so then what should we be focusing on? Should we be focusing on the question, the variables in the question, or should we be focusing on the graph?
The variables in the
Okay.
question.
Um, but so, what was your uh, were there was there any other kind of immediate response to this question? Did you have an immediate response, whether this is a function or not?
I was thinking, yes, it is a function.
And was that your first response?
Unfortunately, yes.
No, that's okay. No, I want you to be honest. Does anyone have a different first response that no, this is not a function?
Yeah, I thought no at first, like before I read the labels,
Okay.
I guess.
Who's that? Is that Ashley?
Yeah.
Why did you think no at first?
Because normally, like before I read the axes, I thought like the bottom would be time, and then so there was going to be like multiple outputs. If that makes sense.
Okay.
But the input. But then I looked at like the graph.
Okay. So what are we getting at here? Looking at this graph. So is this graph the graph of a function? What's going on here? So what's anyone think about the vertical line test? Does that come to mind? Donna, so you saw that, and what'd you think?
I thought it wasn't a function because at like um, at one point it would hit the line at like 3 different places.
Right. So the idea, you're looking at this graph and you're saying, okay, so for this value we get multiple, and that's what Ashley said too. You get multiple values of the dependent for the independent. So is that how we answer this question then? And I think we said earlier that, so wait a sec, this is not time, right? So, and if this were time, is this a possible graph that we could have? Does that make sense? As time being the independent variable and this being the graph, could that work? Angel, you say no?
No, because you can't be at several different heights at the same time.
Right, and time is like linearly forward kind of thing, right? So how could this be time if we get here and then it's like, what would this mean coming through here in terms of time? Like, this or like this part of the graph?
It's like moving back, which is like if it's point A, like you'd think it'd be like the first thing.
Right. So this is impossible, right? So if this were time, this would be an impossible graph to occur. All right. So this graph is trying to graph what relationship? And we're saying, so this graph is not the graph of a function. Are we in agreement about that? And what relationship is this showing that's not a function? The graph. As related to what? So the graph is showing what as related to what? We can't see as a function of because it's not a function of, right? But we could say it's trying to show one quantity as related to another. What is that? What is it showing?
Would it be the height above the ground in feet to the ground?
As related to the ground? So that's not...
Or I guess like from the point.
So height in feet as related to what quantity?
Could it be like position?
Well, okay, be more specific. So this quantity is what kind of position? Because height is position, right? That has to do with position.
Is it like the position along the path?
So what would different values of this, whatever this axis is, what would that represent? This is height, right? So it's like the vertical axis is height, and what is the horizontal axis showing?
Would like the origin of this graph be like the bottom left corner of the wall?
Okay, sure. That's a corner of the wall, sure. Okay.
So then the ground axis would be how far from the bottom left corner?
Is that what this quantity is? How far from the corner? So that's what
Or
this.
how far from like the leftward edge then?
And what is the left edge called? What is that? I mean, you just said this was the wall. So, or the left edge of the wall is what you're saying?
Yeah.
Yeah. So it's just like horizontal position, right? It's like how far over you are, or distance from the edge of the wall, the horizontal distance. And that's a function or no?
No.
Not a function, because for a particular horizontal position, the caterpillar takes on, so for some horizontal positions, the caterpillar takes on more than one height. Okay, and then, but what about the question? So then, did we decide that the question is or is not a function? So this is height, right? So this graph is not showing, it's not showing this relationship. Is the caterpillar's height a function of time elapsed? Yes or no? And then what's the reasoning behind your answer? Elizabeth, what do you think?
I think that it's yes, because like we were talking about earlier, like the caterpillar can't go back in time.
Okay.
So it's like going like forward, but then also we don't have like any other like thing besides this graph to tell us like about the time.
Okay. Yeah, we don't. Yeah, we have the heights of the caterpillar, but we don't have any. We don't know at what times the caterpillar was at those heights. But can we still conclude for sure that it is a function by reasoning about about time and height?
I think we can
Who is that?
because
Go ahead.
because we can't because the caterpillar can't be at like two spots at once,
And when you say spots, you mean what?
like places on the wall or
Okay.
heights.
Right.
But at any one time, he's
That's
going
right.
to be at a specific
Right.
height.
Given every value of time, what's true? There's only one height the caterpillar could be at. Okay? It's like she said, the caterpillar can't be at two heights at once. So yes, that is a function. Okay? This graph is not showing that relationship that's being asked about. It's showing height as a relationship with horizontal distance, which is not a function. Okay? But this is because at any given time, the caterpillar can only be at one height at any instant of time. So that's the idea of a function. You get one output per every input. Okay, so all right. So now that we've established that, I'm going to throw a wrench in this. I'm going to come back to this curve and say, I contend that this curve could be a function if we just think of it a little bit differently. So how could this curve still be thought of as a function? Even though we know this relationship is not a function, is there a way to conceive this curve as a function? Any ideas? And I'm not putting any limitations on what variables you have. It's just that the curve itself is the only requirement, right? So
Can you think of it as just kind of like the path the caterpillar's on?
okay, so what variables? So a function is always about variables. So what variables are you thinking about?
Not sure.
So we need an independent and a dependent such that given any value of the independent, whatever that is, there's only one corresponding value of the dependent. And this curve is a representation of that relationship.
Could you do like time and position?
Okay, let's try that. So let's make time be the independent again, given any value of time. And then position would be comprised of what? So when you say position, what do you mean by that?
Like relative to where the caterpillar started.
Like distance from point A? Is that what you mean?
Yeah.
Yeah, that could work, right? So that would work. But although then the distance from point A is a quantity that's not being shown on this graph, right? But that's true. The distance from point A at any given time would be a function. So I want to get back to this curve being a real representation of what we're talking about. But that's true. That would be a function. So how do you designate the position of the caterpillar? Say right there. What does it take to designate the position on the wall?
Now, when we're talking about position, are we talking about a position as a function of time?
So yeah, we're going to try our independent variable is going to be time. So you said time and position, and that's actually correct. It's just the question is, how do we designate position? What designate?
Use the height above the ground.
Okay, so then we're back to this function.
Yeah.
And that's only height. So what else do you need for position? So that we make this curve.
Is it going to be two variables, like the horizontal distance and the height above the ground?
Right. So to get position, we need both, right? We would need horizontal and vertical height. Would that be a function then? So it's like our dependent thing now is actually two variables, both varying with t. Is that a function? Given any time, is there only one, say, pair of values, or is there only one position? Is there only one position for every time? Yeah, and it's so I should have said dependent is position, which is comprised of horizontal and vertical quantities. So dependent is what Angel said, position, and to designate position, we need two quantities to do it. We need a horizontal at that time and the vertical at that time, and that gives us a particular position. So this is the idea of this, and it is a function. So this curve is a function if you think of it as there's only one place on the wall the caterpillar can be given any time. But that place needs two quantities, a horizontal and a vertical distance, to designate that position. So what is this about? You've seen this before? So it's like this. Right? So our input is t, and our output or dependent variable is actually a dependent thing, is actually a pair, right? A pair. And what is this? Remember what we call this? What kind of function this is?
Parametric.
Yeah, it's a parametric function. So by defining, so we have this parameter t, our independent variable actually does not show up in the graph, right? The t value of t doesn't show up unless I come here and for each point I label what the corresponding t is. But there's no t-axis, right? There's no t-axis. There's just we're graphing the dependent thing, right? Which is now a pair of quantities. So that's the idea of a parametric function. So we can get all kinds of crazy graphs that before we didn't think were functions because they weren't functions of, y was not a function of x, but ordered pairs, right? Ordered pairs could be a function of some third quantity, which is called the parameter t. Okay, so does that make sense? So we can see that curve as a function if we think of it as position as a function of time, but position requires two quantities. So then we can get, so what about this? Is this a function or not? Yes or no? Is it a function?
Yes.
Yes. Why is it yes a function?
It's a function of the parameter t that gives the position of each ordered pair.
Yeah, so you can get ordered pairs as a function of t. Could you also answer no to this? When I asked you, is it a function? Could you also say no?
Yes, as well.
Yeah, how is it? So how is it not a function? Somebody knew. How's it not a function? What would you say to say, oh, this is not a function?
Could you say that y isn't a function of x?
Okay, what do we think? Is that right? Y is not a function of x. Right. Yeah, right. So there are values of x for which you get more than one value of y. So right, y is not a function of x, but we could say ordered pairs are a function of t according to this rule here, which is in this way. Okay, another one. Complicated function or not so complicated? What would you say? Is complicated function or not? Here's what it is. T plus sine 2t, t plus sine 3t. It's not that complicated, right? But it's because it's a parametric function that we can get a crazy looking twisty curve like this, right? So if we tried to write this y as some relation to x, it'd be very complicated, right? It'd be a very complicated equation, but with a parametric equation, this isn't so bad. T plus sine 2t, t plus sine 3t. I think this is a fun one. I like this one. It reminds me of some kind of fish. All right, so that's cosine t and then sine of t plus sine 5t. Okay, what about this one? Is this a function? How about this one? Is it a function? Yes or no?
Yes, it is.
Okay, Richard said yes. Tell me more.
I think it could be a case where y is a function of x as well as a parametric function.
He's saying both now. So here y is a function of x and also position is a function of t. So if y is a function of x, can we determine what that is? Here I'm giving you, here's x is 1 plus 3t. And y is 2 minus t squared. So is y a function of x? And if so, what is it?
Am I allowed to answer?
Somebody.
Oh, okay.
Sure.
2 minus the quantity of y is equal to 2 minus the quantity of x minus 1 over 3 squared.
So what are you doing? Tell me what you're doing.
Sorry. I'm writing x as t as a function of x, I guess. So I'm subtracting 1 on both sides and dividing by 3.
Okay. So
And
that's
then,
true and that's true. Okay.
And then I'm taking that and I'm plugging it into the y equation.
Mm-hmm. So you probably remember doing these types of problems where you're resolving a parametric function into equation of x and y, and so, but this, we're kind of talking about it in the context of, is y a function of x? And so that by doing that, we can show, yes, y is a function of x. Given any x, you're only going to get one y back. And so I could come here and type that in, y equals 2 minus quantity x minus 1 all over 3 squared. And so what should I see? They should be right on top of each other, right? So just the parametric version, y is a function of x, both of them. So the same set of points. Now there's a difference though. You get the same set of points, but there's another major difference to this. Does anybody know what that is? It has to do with t. So with t, with the parametric version of it, so given a value of t, say t is 1, what do we get? 4. Looks like we get the point 4, 1. See that? So we get the point 4, 1, and that comes from t being 1. And then if t is 0, what do we get? 1, 2. Oh, 1, sorry, 1, 2 is here, sorry. That's 1, 2, and that's for t equals 0. So what does the parametric version have that the other function doesn't? T equals 0 is here, t equals 1. So where would the point for t equals 2 be? Would it be over here, or would it be back over here? Exhibit A or exhibit B? I thought that was an easy question. Yeah, so t equals for t equals 2, the point's going to be somewhere over here, and then t equals 3. And so what is this implying? T equals 4, t equals 5. What does this imply about the parametric version?
As t is increasing,
yeah,
the curve is being traced in a clockwise.
Yeah, so there's a direction, right? So there's a direction for increasing t. So for increasing t, you have a direction to the curve. Okay. Most of that you've seen before, but I wanted to kind of give you that in the context of functions, right? So what's a function, what's not a function? So in this world, this parametric opens up this whole world of curves that could still be considered functions. You can pretty much have any curve in the plane and still be thought of as a parametric function. That position is a function of t. Okay, let's look at that. So I want to look at, is it this one? Yeah. All right, so I want, what about a circle? Circle, is a circle a function? Is a circle a function or not?
Yes.
Who said yes? Is that Donna?
Mm-hmm.
How is it a function? How is a circle a function?
If x is cosine of your input.
Okay.
And y is sine.
So x is cosine. Let's do this here. So, all right. So she's saying yes, it is a function. Any way that it's not a function?
Y is not a function of x.
Okay, y is not a function of x, right? Because for every value of x, there's potentially 2 values of y. So to do parametric functions in GC, you do control 2. When you do control 2, it just pulls up an xy vector like that. And then you say equals, and then control 2 again. And now you put your functions of t in. So you're suggesting what, Donna, for a circle?
Sine of t or pi or theta.
Okay. Yeah, so t, so lowercase t is built in as a parameter for GC. So you want to do sine of t and?
Sure. Cosine of t. Wait, no. Flip it.
Flip it?
Yeah.
Yeah, so this will still give a circle, but our convention is, the definition of cosine is x coordinate, so let's go with that. And the definition of sine is y coordinate. All right, so I'm going to plot this circle, and here we go. And what happened? So I thought we were supposed to get a circle. Did we get a circle?
Is it because of the domain of t being limited from 0 to 1?
Yeah, right. So if you look over here, whenever you use t, whenever you use t, it'll pull up. You'll have a little section over here. It'll show you what t is ranging from. So can you see that that's very faint? But you can see it's ranging from 0 to 1, right? So this is 0 radians to 1 radian. So I want to graph the whole circle. How can I graph the whole circle? So one thing I could do was just change the range of this. I come up here and just change that. And what do I change it to?
Pi.
2 pi. So when I change it to 2 pi, I get the whole circle. But if I want to graph, maybe I want to graph more than one or multiple parametric functions on the same graph, each one might have its own different range, but I'm only allowed one range of t in the particular file that I have. So I want to, rather than fiddle with this, I want to keep this 0 to 1, and I want to do it a different way. So how can I get... What happened? What's happening here? There it is. How can I want to show the whole circle, but I want to keep the range of t from 0 to 1. Any ideas? So I'm thinking as t goes from 0 to 1, what do I want to happen here?
Maybe like work 2 pi into your cosine and sine.
Okay, so right, exactly. So this is called the argument. So what the whole thing that's you're taking the cosine of is called the argument. So as t goes from 0 to 1, what do I want the argument to do?
Go from 0 to 2 pi.
Very good. Okay, so is that a familiar kind of thing? So as t goes from 0 to 1, then I want the argument, say of cosine and of sine, to go from 0 to 2 pi. Is that familiar? Does that sound familiar to anybody?
It's the morphing thing you showed
Remember the
us.
morphing thing? Yeah, so now this one's easy because you don't even really need the morphing thing because they both start at 0, right? So what could we do to the argument here?
Change the argument to 2 pi t.
Yeah, it's kind of basic, right? Because so like when t gets up to 1, you want it to be 2 pi t 0. So this is kind of you don't really need the morphing operator in this case. But if this were something more complicated, like it didn't start at 0, if it started at something else, it'd be a perfect chance to have the argument of cosine and sine be the morphing operator, and then it would just be an easy way to change that expression so that you know that when t goes from 0 to 1, your argument's going to give you the range of angles that you want. Make sense? Okay, so now when we graph it, it works, right? We got the whole circle. Okay, what about... this way. Okay, is this a circle? What about that? Is that a circle?
It still is a circle no matter how you shift the view of it.
Okay.
The radius is still the same.
So yeah, what makes it a circle?
If it has the same radius. Okay.
From the center.
Yeah. So if every point, so the definition of a circle is not that it looks like a coin, or it looks like a perfect circle that we're used to. The definition is that given any point on the curve, what's true?
It's equidistant from the center.
Yeah, every point has the same distance from the center, and then that's going to be true. Just stretching the axis isn't going to change that, right? So yes, that's a circle. So can we prove that? How can we prove it's a circle? So what you just said, right? What you just said, every point is?
Could you use the distance formula?
Okay, tell me. With what? So which point should I pick on the circle?
Can you just use like the formula?
Well, so you've got it, yes, but you've got it. So the idea is that you're picking any point on the circle, right? We're not picking a point on the circle. We have to represent every point on the circle. So what is every point on the circles? And that's just an example.
Cosine 2 pi t, comma, sine 2 pi t.
Uh-huh. Good. And what is so given any point on the circle on the curve, we're proving it's a circle. So what do we want to do with that?
Find the distance between that point and the center 0, 0.
Distance to 0, 0 is? What is it?
1.
Okay, we gotta show that.
Or like the formula.
Yeah, so how are you gonna show that?
This would be where the Pythagorean theorem comes in.
Okay. Tell me.
So to find that would be you have to show that cosine of 2 pi t squared plus sine of 2 pi t squared is some constant.
But
like some radius,
but the first what we're saying is what is the distance, right? What is the distance from 0, 0 to that point?
It would be okay, it's the square root of cosine 2 pi t minus 0 squared plus plus sine 2 pi t minus 0 squared.
Right, so yeah. And what's that? Cosine squared of an argument plus sine squared of the same argument.
1.
That's 1, right? Pythagorean identity. Therefore, every point, if this is every point in the circle, then every point is a distance of 1 away. Thus, it's a circle. Okay. So let's do a little activity here. So we're going to build, like I said before, sometimes you want, right, multiple curves in the same graph, and you don't want to, you might need a different range of, say they're based on circles, you may need a different range of a t for each curve that you're drawing, but you're only allowed one range of t at a time in a GC file. So we will just keep that range of t from 0 to 1. And so this is just a review. So like how would I make the circle bigger? So let's go back to making it look like a circle. What do I do? Now suppose I want this circle to be radius 2.5. How do I change the circle to make it radius 2.5?
Multiply 2.5 in front of each one.
Yeah, so we want the x-coordinate to be 2.5 times as big and the y-coordinate to be 2.5 times as big. Okay, so let's look at this then. So we're going to start with this circle. I'll turn the old one off. Okay, so I got a circle there. So we want to write this circle parametrically, and we want to use the range of t from 0 to 1. All right, so maybe have you guys work on some stuff together here. So sketch this circle. And then we also want to show in the same graph this. Okay, so sketch that. Make sure you take a screenshot. So if you can take a screenshot before we do breakout rooms. And then in the same graph, we also want to sketch this. And you can think about doing that in two different functions, or maybe you could figure out a way to do that as one function. And then see if you can do this much, and then we'll add one more difficult element at the end. So let's take let's do 10 minutes to see if in 10 minutes in your breakout rooms you guys can reproduce this with t varying from 0 to 1 for all functions. And you want to reproduce this.
Cosine 2 pi of t.
Okay.
And then y is 1.5 sine 2 pi of t.
Can't find there it is. Sorry. And okay, so you said, so the red is, the black, did I say the black circle?
Yeah.
Okay, so the black circle is, you said, x is?
1.5 cosine 2 pi t.
And
then y is 1.5 sine 2 pi t.
The rest of you agree with that? Okay, let's do the red smile next. Who was able to do the red smile, keeping t from 0 to 1?
I have an idea.
Okay.
So it's going to be just tell you x and y what they're equal to. X would be equal to cosine of 5 pi over 4 times the quantity 1 minus t.
Okay.
and then we add 7 pi over 4 times the quantity t.
Times t?
Yeah.
Okay, so what's going on here? As if t is 0, then we get what?
0, we just get cosine of pi over 4.
5 pi over 4. So that starts here, and then t goes from 0 to 1, and when t gets to 1, we get?
Cosine of 7 pi over 4.
Did other teams get this? Just come up with this? So this is our morphing operator, right? A times 1 minus t plus bt will morph from A to B as t goes from 0 to 1. Remember that? That's exactly what we want. We want the angle measure to start at 5 pi over 4 when t is 0, and then be at 7 pi over 4 when t is 1, and then everything in between. So was there another group that was able to do that? So when it comes to animations, I'm telling you, the morphing operator, super helpful. So if that wasn't, it didn't feel ready on your fingertips, like it was like you don't remember that, then please remember that. This is going to be like for your projects. Don't forget that really helpful tool, because you just plug and play, right? You just, whatever you want to be at t equals 0, you just put it there. And this could be a point, it could be a value, it could be a function, right? So we saw all these different like modalities for this too. It wasn't just, so here we're using it for a value, right? We want the value to morph from 5 pi over 4 to 7 pi over 4. But I showed you how a function can morph into another. And you can morph, here we're morphing values, we can morph one point to another, and that gives you the line in between. Okay, how about the eyes? So was there a success getting the eyes? So we know it's going to be x and y. Any success? Is that no? Did anyone come up with this? So we're just thinking about points, right? Thinking about points on these segments. What is x and what is y?
Y would just be 0.5.
Yeah, y is just always 0.5, right? No matter what t is, right? It's not a function of t. No matter what t is, it's 0.5. So then what about x?
Would it just simply be the quantity 1 minus t times 0.5 plus t times 1?
Yeah, so we want x to go from 0.5 to 1, say as t goes from 0 to 1. So can we set it up? So Richard's got it. Can somebody else tell me what would we write so that as t goes from 0 to 1, x goes from 0.5 to 1? Somebody new. Elizabeth, Yasra, could you do it?
Wouldn't it just be 0.5 times 1 minus t plus 1 times 2?
What do we think? Richard, is that what you said?
Yes.
Yeah, so when t is 0, you're going to get 0.5. When t is 1, you're going to get 1. See how that works? T is 0, that makes this thing 1, and you get all that, and none of this. When t is 1, that makes it 0. So this is gone, and you get all this, and then in between, you get everything in between. So that's it. And then you can, I was going to say, we might be able to use absolute value to do both at once, but you can't do that because x is your dependent thing, right? So I don't know, that might work. Anyone try that? Anyone try putting in absolute value of x? Remember we saw that before with the heart and we were doing the regions? I don't know if that will work or not. But here, let me try. I'm curious. So when I do the control 2 for this x, do absolute value. That might work. let's see, equals 0.5 times 1 minus t plus t and 0.5. And we'll go back and turn off the eyes. Oh, that's too far back. All right, that's fine. All right, so let's. Can't grab equations of this form. It doesn't like it. So it doesn't like this thing here. Can't do it. So we gotta do each eye separately. So then y else to be 0.5, and then you're going to go from whatever, -1 to 0.5. Or you could go -0.5 to -1, whatever. All right, so then there's the any questions on that so far? All right, so there's a last part to this, which is more challenging. Unfortunately, we only have 5 minutes left. So maybe we'll get started and we'll make this a little task for you. So here's the last part. So, what's going on here? So actually what's going on here is, this is based on, so I have to tell you this is based on a circle where this is actually the center of the circle here, and this is the left endpoint. So the left endpoint is at -0.3 and about, it's not quite -1. I don't know what that is. I don't know, -0.95 or something. We'll call it that. All right, just to have something. Okay, and so then the center here is at, or is it? I'm sorry, so -0.25. So this is -0.25. And then the center is at 0.25, -0.95. There we go. All right, which means that there's another point out here, and we're going to do this based on, and so then right. So this is kind of like, so there's this kind of reference circle. Try that again. Okay, that's better. There we go. There we go. Okay, so there's this reference circle that's happening here. And what we want to think about is, if you think about x and y separately, this is not so bad, okay? Starting here, what does say the x coordinate do? Starting from here, to draw this whole curve, what does x do to draw the whole curve? Just looking at the x coordinate, do you see what it does?
The angle measure goes from pi to 2 pi.
From pi to 2 pi, is that what the x coordinate does? From pi to 2 pi?
Well, the coordinate itself, or
so here, so like if you were traveling along this, think just the x coordinate goes to here and then goes to here, just the x coordinate. So he's suggesting that x goes from pi to 2 pi. Agree with that, or want to change it? X goes, so think of just the X coordinate. Anyone want to revise that? What if the angle measure for x went from pi to 2 pi, where would the curve end? Where would the curve end relative to the circle?
Back where it started.
It would go, if it went from pi to 2 pi, it would end up back where it started?
Pi, 5 pi over 2, right? An additional rotation.
So the x coordinate moves all the way from left to right, and then is it done?
And then back.
Is it done?
No.
Then it goes what?
Another pi 2 radians.
Back.
2 radians.
Right. So it's like it's the x coordinate for angle measure is going, what, 3/4 of the circle like this. Do you see that? From this point to this. What about the y coordinate? So instead of pi to 2 pi, it would be pi to, so 2 pi plus pi over 2, right? So it's starting at pi. The x coordinate goes all the way across to the other side of the circle. That would be half, that would be the 2 pi. But then it also, by the time it gets here, it also does another pi over 2 back to the middle. Thinking about just x coordinates. What about the angle measure? It's the angle measure for x is this one. What about for y? What would the angle measure for y do going from here, this point to this point? So now we're thinking up and down, right? So it starts at the midpoint, it goes to the, down to the min here, and then back to the midpoint for y, up and down. So what angle measure would that be? Starts at the left, makes it down to the bottom, to the lowest point, and then back to the mid.
That would be pi to 2 pi.
All right, so Richard's the only one speaking up. Is this making sense to everybody? Can you see that? Can you isolate x and y? The angle measure for x, we're starting over here at the left at pi, and we make it for x, we make it all the way to the right, but then also it makes it back, like thinking about going down the bottom of the circle and then back up to the top of the circle for just the x coordinate, of that. For the y coordinate, it makes it down to the bottom and back to the middle. So for our range of t from 0 to 1, we need x to do that, and we need y to do that as t goes from 0 to 1. Does that make sense? And then you got to get the radius and the center right? So now you got to get the center of the circle here, and you got to get the radius right, and you're going to build that into it as well. So if you can see this as x going from left to right back to mid, in other words, transversing this range of angles, and y going from what, left to bottom to right, or sorry, mid to bottom back to mid, that's pi to 2 pi. And those are happening at the same time, right? So that as t goes from 0 to 1, that's what's happening at the same time. So that'll be a little task for Thursday.